Section 16.7 in Thomas's textbook, which is the same as 16.8 in Stewart's textbook. It's about one of the three important theorems in multivariable calculus known as Stokes theorem. Stokes was an Irish mathematician and physicist, and he was a professor at Cambridge University. Stokes theorem is the higher dimensional version of Green's theorem. So recall that Green's theorem was if your boundary of the region is positively oriented, piecewise smooth, simple closed curve, where R is bounded by C, then the line integral over the vector field was equivalent to double integral as partial of q with respect to x minus partial of p with respect to y dA, where the vector field was the x component was this function p, and the y component was that function q. So the theorem goes as follows. This is the Stokes theorem. Let us be oriented, so that means the normal doesn't change its direction, piecewise smooth surface that's bounded by a simple closed piecewise smooth boundary C with a positive orientation. Notice all these conditions must satisfy. Let F be a vector field whose components have continuous partial derivatives on an open region in R3 that contains S. Then the line integral for over a vector field becomes the surface integral time of the curl of f dotted with s. So this is like the curl of f dotted with s, where ds is the surface area element vector, which is n, that's like unit normal, the normal vector times ds. Note the orientation of the boundary depends on the orientation of the surface. So ds vector is the same as n times ds, but n is the same as cross product of the these two vectors, provided the surface has been parameterized in terms of the parameters u and v. So you take the partial of r with respect to u, partial of r with respect to v, divide by magnitude. So this guy gives you unit normal vector. But ds is also cross product of the magnitude of ru, rv, dA. That's the definition of ds. But these guys cancel. So all you get is line integral over a vector field can be replaced by double integral of curl of f dotted with the cross product of Ru and Rv, which u and v happens to be the parameters which they define the surface S. So this is it. Now the special case, if z is an explicit function of x and y, then we move this guy over and set it equal to 0. We call that function capital G. And the gradient of G happens to be can replace this cross product right here, provided the surface, the equation of the surface looks like this, which is explicitly in terms of x and y. So in other words, the gradient of what we call this a zero level surface is pointing in the same direction as the unit vector, as the normal vector to the surface. You can also go the other way around, depending whether the normals are pointing up or down. So here, I guess it's open up. Here is the normal is pointing down, can replace that product. So therefore, this equation, this double integral becomes this, okay? Stokes theorem is valid for sphere, torus, or cube, or tetrahedron. Tetrahedron, a four-sided pyramid. So what Stokes theorem says, it says the integral of a normal component of of the curl, which is vector field, over a surface S is equal to the integral of the what? Tangential component of F, what? Around the boundary of C. In other words, line integral can be replaced by what? Surface integral, but that would be what? Of curl of F dot with normal vector. So now let's see a problem and see how Stokes theorem applies to a what? Line integral in higher dimension. Remember, in two dimension, if F was in two dimension, like, function of what? P and Q, then we could use what? Green's theorem. But however, the question is, how does the Green's theorem apply when the function vector field is what? Three-dimensional. Well, that's where the Stokes theorem comes in. So remember, line integral of over vector field F now becomes curl of F dot ds, but this would be a surface integral. But notice the vector field now is in what? In R3, not in R2. Remember, this is called P, Q, R, or some books, they call it M, N, I don't know, maybe R. So the C, the curve C, is the triangle with vertices 1, 0, 0, 0, 1, and 0, 0, 1, excuse me, and oriented counterclockwise as viewed from the top. So this is it. So immediately, because you know the surface hits the what? X and Y and Z axis at once, so that looks like a plane, so the surface is a plane. And this is the equation of the plane, which is x, y, z, and you can tell by the inspection the normal is 1, 1, 1, right? Because the normal vector, the components of the normal vector to a plane are the coefficients of x and y, correct? So let's do it the direct way, which is what? Evaluating this, the left side, and then I will do the Stokes theorem. These answers should match. So let's do the left side. To do the left side, I have to split the line integral into what? Three separate line integral because I have three edges. So I got to go over C1, do the line integral over C1, then C2, then C3. But before I do that, I have to parameterize each of these curves, boundary curves. They happen to be a line segment, so it can't be that bad because all you have to do is what? For instance, to write the parametric equation of C1, just write the initial point times t, the parameter t, terminal minus initial, that would be the vector parallel to the line. Work this out, add them up, you get this. 1 minus t, t 0, t goes from 0 to 1 for all cases. Because we're dealing with what? Line segment. So please refer to chapter 12, section 5, or one of those sections when we talked about equations, the parametric equations of a line in R3. So now I have to kind of like what? For each curve, express this vector field in terms of t. So go from there. For instance, for C1, remember x is 1 minus t, y is t, z is 0. So here I have to replace x's with 1 minus t, y's with t, and zeros with z's with 0. And I get this. However, I have to dot that with dr. dr is the displacement. So if this is r, okay, r1, dr1 is the derivative of the sky, which is negative 1, 1, 0 dt. So that goes right here. And t goes from 0 to 1 for all cases. So I have to continue this for C2 and C3. There it is. Remember, you have to express the vector field in terms of what? The components of the curve, like in this case for C2, dotted with dr. This is the dr displacement. Remember, r was 0, 1 minus tt for r2. So dr is 0 minus 1, 1 dt. And t in all the cases go from 0 to 1 because we're dealing with what? line segment. So what you do, you evaluate these line integrals, so you get 3 answers for each. And in this case, it turns out all answers match. And if you add up all these negative 1/3 3 times, you get negative 1. So now let's see how Stokes theorem applies. First, you get the curl of f, which is a vector, right? So the first row is ijk, the second row is blank partials, and the third row is the x and what? Y and z component of the vector field PQR. Okay, when you perform this, you get this vector. Then I have to dot it with what? A normal vector. Remember, the normal vector to this plane is 1, 1, 1, 1, 1, 1, 1. Take the dot product of the curl and the normal vector. Lo and behold, you get this double integral, right? But remember, the projection of the plane on the floor is just a line here whose equation is x plus y equals 0. How do you know that? Set z equal to 0, you get x plus y equals 0. And take the what? Element what? Vertically. So therefore, what? When you take the dot product, you get negative 2z minus 2x minus 2y. Replace the z with 1 minus what? X minus y, correct? And then y goes from 0 to what? 1 minus x, and x goes from 0 to 1. Evaluate this, and guess what? You get negative 1, as we did when we did the line integral over the vector field on curve C1, C2, C3. In other words, up there we had to repeat the line integral 3 times, but the minute we applied the Stokes theorem, we just had to apply what? Evaluate the double integral once. So it really makes the job lot easier. The next problem is also similar to what we did last. So here is the vector field, minus 2yz, yx. And S is part of the what? Elliptic paraboloid, which opens downwards, right? And lies above z is equal to 1. So here's the plane, here is this elliptic paraboloid. It's above the plane, but below the what? Elliptic paraboloid. The intersection of these two curves happens to be a circle with radius 4. So if you shine a light, like here it is, here is the what? Plane. Here is the elliptic paraboloid. Notice the intersection is a what? A circle. That circle has equation x squared plus y squared equals 4. So it's a circle radius at the center, and the center is at the origin, and the radius is 2. So this is the curve. So parameterize what? The curve, this curve. So it's 2 cosine t, 2 sine t, 1, because what? The z, where the intersection happens, is equal to 1, because this circle is on the plane, all right? So that's why z is equal to 1. So now, to evaluate this line integral, I'm going to use the Stokes theorem. First you do it the direct way, which is, parameterize the what? The vector field in terms of what? Parametric equation of the curve. Remember, this is your x, that's your y, that's your z. And then dot it with what? dr. So take the derivative of this guy, which is what? Minus 2 sine t, 2 cosine t, and 0. And that's where I got that, dt. And t goes from 0 to 2 pi, so the answer is 8 pi. Now let's apply what? Stokes theorem. So find the curl of f, you get this, okay? Now I need to find the normal vector to this elliptic paraboloid. How do I do that? I move the what? 5 minus x squared minus y squared to the left side. You can also what? Move the z to the right side. Call that function capital G. Set it equal to 0. So this is a 0 level curve. So the gradient of g is in the same direction as the normal vector to the surface, which in this case the gradient of g is 2x2y1, So take that and dot it with curl, and lo and behold, you get this double integral. And now what I did at this point, I changed the problem into what? Polar coordinates. So wherever I see x, I replaced it with r sine theta. Wherever I saw y, I replaced it with what? Excuse me, x with r cosine theta and y with r sine theta. And I have replaced the dA with r dr d theta. Because the projection is a circle, radius 2, center at 0, 0. So r goes from 0 to 2 and t goes from 2 pi. If you evaluate this mess, you get 8 pi, which is precisely the same as what we did when we did it the direct way. So Stokes' theorem kind of like eliminates what? All those computations, specifically if you have multi-curves. In other words, the boundary is union of what? A whole bunch of what? Smooth curves, which you saw the example of that in the previous example. So that's basically the beauty of Stokes' theorem. Let's make a quick comment about Green's theorem. Remember, Green's theorem was line integral equal to double integral, what, partial of q with respect to x minus partial of p with respect to y dA, where f was p of xy, q of x. So where did this come from? Well, if you apply the Stokes theorem for what? For function of two variables, okay? So when it comes to what? The what? Third component of the what? Vector field, replace that with 0. So there you go. And because we are on the what? XY plane, so the normal is 0, 0, 1. So anytime you have a region bounded by a curve on the floor, you know for sure what? The normal pointing up along the z-axis, which is 0, 0, 1. So take that curl, dot it with 0, 0, 1, and lo and behold, you get what Green's theorem said. So that's the consequence of a Stokes theorem. I hope that helps to clear this formula, which we learned way back about Green's theorem. Where exactly this difference come from? Well, it comes from a Stokes theorem. Thank you.